Hello, everyone. My name is Vladimir Gurevich. I'm the founder of Piforica. And here with me, I have Shaan Nagy and Ali Kheradmand that will be presenting a very interesting topic, automated switch validation with path complete testing at scale. Ali is a senior software engineer at Google, working with network infrastructure organization. Prior to that, he received his PhD from UISC with research focusing on enhancing the reliability of systems and networks through automated reasoning. And Sean is the fourth year PhD student at UCSD. He's studying programming languages under Professor Loris de Antoni. His main body of research focuses on formal analysis of incomplete programs to make code generation more reliable. He interned in Google this past summer and worked with P4-based automated reasoning team uh, where he worked on using symbolic execution of P4 programs to generate tests for network switches. So very exciting topic. Please welcome Shaan and Ali, and let's see their presentation. Thank you.
Thank you. Thank you, Vladimir. So just a quick note that I will only take 3 to 4 minutes introducing our team and providing the context for Sean's presentation, and then Sean will present the meat of the talk, which was his uh, internship project while he was at Google this summer. So let's get started. We are from a team in Google that is called P4 based automated reasoning team, or P4 bar for short. And our goal is to increase the reliability of Google's network infrastructure using techniques from areas such as automated reasoning, programming languages, and formal methods. Particularly, so far, we have been focusing on ensuring that our networking switches work as expected before we deploy them into production. One of the products that our team has developed is called Data Plane Validation as a Service, or DWAS for short. That is a library that facilitates testing and validation of switch packet forwarding behavior with focus on its functional aspects. One of the most important tools that the library uses is a tool we have developed that is called P4 Symbolic, which in short is an automated P4 model driven coverage based test packet generator. And I'm going to tell you what that means. Concretely, P4 Symbolic drives a set of test packets from a formal specification of how the switch should work. And the benefit of that is that this way we get guaranteed comprehensive coverage automatically. And if the specification changes, we can effortlessly regenerate the tests. So we use P4 as the specification language of how the switch should work. And the way that we use it is that we take this P4 model that basically describes our expectations from the switch. And we also take a set of table entries from a historical snapshot of one of our switches that is in production. And then we give these two things to P4 Symbolic along with the coverage goal that we want to be achieved. For example, we'll tell it to provide a set of packets that together they cover all tables in the snapshot, all table entries in the snapshot. That means that for any table entry, there is at least one test packet that is guaranteed to hit that table entry. Then P4 Symbolic goes and does its magic and produces a set of test packets. And from this point, we do two things. First, we take those generated test packets and then also the table entries from the snapshot, and we install the table entries on an actual hardware testbed. And we inject the test packets and collect the results. Second, we take the same table entries, the P4 specification, and then we use a P4 simulator, for example, BMV2, and inject the same packets into that simulator as well and collect the output as the expected output. And then we compare the expected and actual output that we got from the actual switch and compare the two. If there is any discrepancy between these two, we report this discrepancy for further investigation. And using this method, we have been very successful in finding and preventing hundreds of bugs before we deploy our switches into production. And we have published some of our results in our SIGCOMM 22 paper in case anybody is interested to read more. So now, despite its success, P4 Symbolic has a lot of more room for improvement, and we are constantly trying to improve it. And in today's session, we're going to talk about one of its caveats regarding its notions of coverage. And there are basically tricky bugs that escape current notions of coverage. And we're going to talk about the problem, our baseline solution to this problem that doesn't scale, and our optimizations that made this approach scales for our needs. And these parts are going to be presented by Shaan. So Shaan, please take it away.
Thank you. Yeah, so as Ali mentioned, we're going to be talking about gaps in our notion of test coverage, bugs that can escape those notions, and then things we can do to catch these kinds of bugs. So circling back to the workflow that was mentioned earlier, I want to drill in on this notion of a coverage goal. For our purposes, you can think of the coverage goal as being something like this. For every table entry T, generate a test packet that hits T. And as Ali was saying, we've met a lot of success with these kinds of coverage goals, but there are bugs that are not guaranteed to be covered by test suites that match this coverage goal. Let's look at a production scenario. So suppose that your P4 symbolic has generated packets that hit the ACL table, and these packets are IPv4 packets. You observe that the behavior is as expected, the tests pass, and so you think that your switch is correct and doing just fine. But if instead you had generated an IPv6 packet to hit the ACL table, then you would have observed a failure. So actually, there's this bug that you observe in the second case and not in the first case. And the thing that I really want to highlight is that this bug only occurs under a specific combination of conditions. It's not enough to have a packet that just hits the ACL table, and it's not enough to have a packet that's just an IPv6 packet. You need both of these things to occur at the same time in order to identify the bug. And this is not just a hypothetical. This is a bug that we actually observed in practice, and it's one that we were very fortunate to catch. So the main problem and the focus of today's talk is going to be how can we catch these bugs that only appear for specific combinations of conditions. So solution, as maybe the title slide has preempted, is to expand our notion of coverage and talk about path coverage. So maybe one naive thing that you might want to do is test every combination of conditions. So you'll say, okay, well, I want a packet that hits these 3 table entries and is IPv6, and I want one that hits these 5 table entries and is IPv4. And you can imagine, specifying ever larger sets of conditions that you're combining in every possible which way. But that's quite infeasible. There are way too many combinations, and you'll end up with a set of tests that you will not be able to run. So what we should be focusing on is thinking about combinations of conditions that are important to test. What combinations do we care about, and which ones do we not care about? Our answer to this question is that we should care about combinations that have different behaviors in the P4 model. So if the P4 model tells us that a certain combination of conditions is handled differently from others, that's a combination that we should be focusing on. In that spirit, we have the following notion of path coverage, which is that we want to generate tests that cover every execution path through the P4 model of the switch. And so in some sense, this is ultimate coverage up to the granularity of the P4 model, because every kind of packet that the switch says we should handle differently, we test. That's the goal of path coverage. So to make this a little bit more concrete, you can imagine you have a switch, a very small one with 2 match action tables, one with 3 rows and one with 2 rows. Now, for each path, for example, this one, through the switch, we'd like to generate an input packet that hits this path if any such input packet exists. So we'd like one for this path, one for this path, one for this path, and so on. So in this little example, there are 3 rows in table 1, 2 rows in table 2, 6 paths. But you might be worried about how this scales. For example, If I have 3,000 rows in table 1 and 2,000 rows in table 2, then I'll end up with 6 million paths. And so you might be afraid that there are some scalability challenges, and there are, but they're not quite as bad as you would expect, because in practice, most of these paths will not be feasible, and that you can't find an input packet that actually takes the path. So for example, here, along this path, the action in table 1 sets egress port equal to 10, and the match in table 2 checks egress port against the value 5. And clearly, no packet will take this path. So this is not a path for which we need to generate a test packet. So even though there are 6 million total paths in the graph, the number of valid paths, and thus the number of test packets that we need to generate, is actually far, far fewer than 6 million. So then the question becomes, how do we explore only the valid paths in an efficient way? So I'll tell you. We'll start with our baseline, and then we'll introduce some optimizations going forward. But the core of the technique is to essentially do a depth-first traversal of the P4 model, and along each path that we explore, we use this technique called symbolic execution to construct a logical formula called a precondition. And what the precondition tells you is what has to be true about the input packet in order for me to take this path. So for this path, for example, the IPv4 value of the initial input packet has to match this LPM match. And then also, it needs to be the case that after I've set next hop to 1, I can match on next hop being 1. So this is just sort of a trivial predicate true. And then for the rest of the path, I'll accumulate more and more constraints. Now, when we have a path and we have its precondition, we can throw this logical formula into an off-the-shelf tool called an SMT solver, which will solve for all of the unknowns in the formula. And then we can take those unknowns and use it to construct our test packet that will then run through our switch and simulator. And critically, right, a key optimization here is that as we're doing our traversal, if we find ourselves in a situation where we see that already the precondition can't be satisfied, so here we have this 1 is equal to 2 because we set next hop to 1, and then we try to take this match next hop equals 2. If we find ourselves in this condition, there's no need to continue exploring extensions of this path because there won't be any input packets that can take any of them. So in this case, we won't continue this path, and we'll sort of backtrack and proceed to the next possible match. So this is the high-level idea of the baseline depth-first traversal algorithm. But unfortunately, it's quite slow. So it took us more than 15 hours to generate packets for our class stage 2 switch snapshot. So we felt that we needed to do something to make this a bit faster. And the first thing we tried is a technique out of the literature to reduce the runtime of the algorithm with some divide and conquer like strategy. So if you're interested in the citation, it's at the bottom of the slide, but here is the main idea. So we can divide our P4 program up into 3 pipelines. First, the input packet comes into the parser over here. It gets processed, and then it proceeds to the ingress pipeline. More processing happens. It proceeds to the egress pipeline, more processing, and then it gets chucked out of the switch. And so what you can observe, if you're keeping in mind this depth-first traversal style of exploration, is that there are 4 paths over here in the parser. And so that means that we're going to have to do a traversal of the ingress and egress pipelines up to 4 times, once for each parser path. And similarly, because there are 4 times 2 equals 8 paths through the parser and the ingress combined, we may have to traverse the egress as many as 8 times. So one perhaps good optimization that we can try is to reduce the number of these traversals so that we're not doing redundant work. The way that we do that, following the literature, is to look at each pipeline individually, apply our depth-first traversal strategy from before to figure out the valid paths just within each pipeline. So for example, here the parser has 3 valid paths, the ingress has 2, and the egress also has 2. And then we merge these subpaths. So for example, for each of the 4 possible combinations of yellow and green paths, we check whether it's possible to have a packet that takes that yellow path and that green path. So here, for example, out of the 4 possible combinations, maybe 2 of them are feasible. And then we can again merge these feasible ingress plus egress paths with the parser to produce valid paths through the entire system. And then we can chuck these into our SMT solver and recover the test packets. And so the critical thing here is that we've managed to traverse each pipeline only once. So we're saving on the redundant work we noted on the prior slide, but there is a bit of a cost because we're paying for these merging steps, which can sometimes be expensive. So how does this perform? Well, we do better generally. We go from timing out in 15 hours to terminating within some number of hours, but still not great. Results on the other snapshots are a little bit mixed, but generally the trend is that we can do faster, but not fast enough. So one observation is that it's still quite slow, but the other observation is that we have 2 million packets over here. And with our current infrastructure, which admittedly needs a little bit of updating, it would take us upwards of a couple of days to run 2 million test packets through our hardware in our simulator. So it's very relevant for us then to try and reduce the number of paths in some way without meaningfully losing coverage. So you can imagine this following sort of situation where you have an IPv4 table like this, and maybe the rest of the switch to the right of the table has, for example, 10,000 paths. Now, if the IPv4 table has 1,000 entries and you have 10,000 paths later on, ignoring cancellations, you might have something on the order of 10 million paths that you would have to explore. But now we can consider, for example, paths that only differ by their choice of table entry 1 versus table entry 2. So maybe path A comes through here. It takes table entry 1 and proceeds. Path B takes table entry 2, but then is otherwise identical to table entry A. And we can reason that if 2 paths only differ by their choice of these 2 entries, then probably they're not going to give us any meaningful difference in coverage, right? So paths that differ only by very similar table entries will probably trigger the same bugs. What that means is that we don't have to treat all of these 1,000 entries separately, and we can instead merge them into something like this. So here, those 2 entries from before got combined into a single entry, where the action is the same, and the match is either the first match or the second match. And so we call this a virtual IPv4 table. And so maybe, for example, the number of entries dropped from 1,000 to 20, and so we end up with a 50x reduction in the number of paths that we have to explore without any significant loss of coverage. So we have a few different criteria for when we want to merge table entries. They're listed over here on the right. One thing we tried is to merge when the action name is the same, so set next hop, and the non-wildcard match keys, so here IPv4 are the same. Another thing we tried is to merge when the action name and arguments are identical. So here, set next hop 1. And then the third thing that we tried is to merge whenever the action names agree. So in this case, like set next hop matches set next hop here, and so we would merge these entries as well. So on our clock stage 1 snapshot, we found that we dropped from generating almost 2 million packets to generating about 16,000, which is a much more tractable amount for us to be testing and investigating. And we managed to generate those packets in about 7 minutes. On some of our larger snapshots, we still observe that generation finishes in a little north of half an hour at worst, and we're generating no more than maybe 40,000 packets. So pretty good news. So now, what came out of this? Well, I guess the internship ended a little bit before we fully rolled this out, but some preliminary runs have already identified some potential new bugs. So in particular, we found this one bug, this one possible bug, that exhibits this sort of combination of conditions thing we were talking about earlier, where there's a discrepancy between the SciP4 model and the switch behavior on inner packets, where the on NCAP packets where the inner packet has a hop-by-hop action options header, and so we're still root causing this, but we're optimistic that we've caught some new stuff, and we're gonna add some meaningful increase in invalidation. So looking forward, some things that we want to do are integrate these new features fully into our data plane validation as a service service. We have a couple other algorithmic ideas we might tinker with to reduce runtime. And then this last one I'll talk a little bit more about. We want to extend our P4-based path coverage ideas to network validation. So in this talk, we said that you can take a network switch, you can explore all the paths of its P4 model, and this is really helpful to validate the data plane behavior of the switch. If you think about a network, that's just a collection of switches. You can imagine exploring all paths of some P4-like model of the network, and similarly trying to get some sort of validation or verification over the network. So one question that you might want to answer, for example, and that we're interested in as well, is this question: does my network obey certain traffic routing policies? So right now, within Google, there's this internal system, we'll call it System X, that takes in a network topology, and it constructs a simulation of that network. It does some exploration over the paths of the network, and then it, based on the results of the path exploration, checks certain properties, certain traffic routing policies that should be obeyed, and then flags any violations. And one thing about System X that maybe we don't like so much is that it uses a sort of internal and incomplete simulation of the switches. And so what this does is it introduces two sources of truth for switch behavior, one being the P4 spec, and two being the internal representation inside of System X. And then also some of the finer grained switch behavior doesn't get necessarily modeled. So what we were thinking is that we can combine what we've done with this System X, and we can use a P4-based model of the network, use some of our path exploration ideas that we've developed this summer, and then verify properties in the style of this System X. And the advantage to doing this is one, that you get one source of truth for switch behavior, so you don't have to worry that your simulated switch behavior differs from the actual P4 spec. And then two, you can model switch behavior at a much finer like granularity when you pull in the entire P4 spec. So that's it for this talk. So today we discussed generating test suites that achieve path coverage for switch data plane validation. We discussed a couple of optimizations for doing this, one being a divide and conquer strategy out of the literature, and two being a strategy of merging table entries together to reduce the number of paths without a meaningful loss in coverage. So we've already identified some potential bugs, and we're planning to integrate this and roll this out into the services that we provide at Google more broadly. So thanks for your attention and everything, and we'll now take questions, I guess.
Well, Shaan, thank you very much. It was quite interesting and useful. I guess it's always interesting if you can take two implementations of the same P4 program and see if their behavior matches. I guess I have a couple of questions about how widely we can use this methodology, what kind of limitations might be there. For example, one thing that I was thinking about is how do you deal with default entries? How do you deal with situations which are maybe covered as exceptions in the parser? And third, probably the most tricky one is how would you deal with the programs that include any stateful elements, such as counters, meters, or registers, where it is much more difficult to model statically, if not clearly impossible?
Shaan, do you want to take this?
I'll insert a part of it. Yeah. So for table entries with sort of like default actions, you can conceptually think of that as sort of just another case down here at the bottom of the table. And so doing a symbolic execution through that extra case is not too challenging. That is something that we do currently in P4 symbolic. For the other two questions, I guess perhaps I'll kick those to Ali.
Yeah, sounds good. I generally I would say that so we have developed P4 symbolic for our use cases mostly inside Google. So although it's available publicly, so anyone can access it. But in our use cases, some of these things that, some of the features that P4 supports, we don't necessarily don't have a use case for. So we do not model those, or we do not really go after those, at least in P4 symbolic. So for example, the very concrete case is the stateful elements. For we don't model notions of like registers. We do model counters, but we don't necessarily support them in P4 symbolic, and we don't validate them using P4 symbolic. P4 symbolic focuses on single packet forwarding behavior, like input output relationship for a single packet. If there is a need, there is no fundamental limitation that prevents us from extending this to supporting stateful things and, for example, so like validating the behavior over a list of packets or a stream of packets instead of just a single packet. But for our use cases where like this just single packet input output relationship is enough for our use cases. Also, for the parser exceptions, we do model parser exceptions, but again, this is not one of the things that we necessarily focus too much on. So usually one of these constraints that we put, even though P4 symbolic models basically parser exceptions, one of the constraints that we put on our input packets that are going to be generated is that these packets pass the parsing phase successfully. So we generate packets that pass the parser stage, even though we could say we could focus on like malformed packets as well, but that's not what we kind of have a use case for. Although if there is a use case, there's no limitation, we can also support that.
Thank you. Thank you. It's all clear. Maybe one follow-up question I wanted to ask you. So you mentioned that you were able to test your system with about 37K packets, if I remember correctly, right?
Yeah.
Do you know like how this number relates to the number of paths through the parser graph? So that we can sort of understand how many, because the parser graphs shows you the number of different syntactically different packets, right? And so it kind of gives us an understanding of the ratio between those different packet formats and the number of test packets that you had to generate.
Yes, I think we had some more detailed numbers internally, but we don't have it here.
Okay.
Shaan,
do you remember anything off the top of your head?
So I believe that, and you can correct me if I'm wrong, but I think that in, I want to say all the cases, there were about 400-ish paths to the parser. Now, I'm not sure how many of those are paths which end in exceptions and how many of those are paths which successfully reach the end of the pipeline and proceed to ingress.
I think all of them actually are the ones that. So yeah, 400 paths within 400 successful paths within the parser. But these do not. Maybe Shaan can like explain this better. So these do not necessarily mean that all of those 400 paths will result like in like whatever is the number of paths in the rest of the pipeline times 400, because many of those paths are dependent on what is the path that is taken inside the parser. So it doesn't blow up exponentially.
Yeah, it just gives us an idea that probably for each packet format on average you had 400 packets generated, and that's a good sort of number that makes sense to me.
Yep.
So have you guys considered any other optimizations to do in the future?
Yeah. So there are a couple of things that we're thinking about. Let me scroll to one slide that demonstrates something like this. So earlier we mentioned that, well, much earlier, I suppose. Yeah, earlier we mentioned that you'll often end up in cases where you set a value and then you match on that value. And just between these two table entries, you can tell that there's no point in trying to pursue these kinds of paths. Now, in a typical DFS style approach, every time you reach this table, you would re-explore this combination of two table entries, and you would rediscover that they're incompatible. So one thing that we're thinking about loosely is ways of like storing or caching this information or merging these kinds of tables or something like that, so that we observe once that this path, these two table entries are not compatible, and we don't have to sort of recompute that observation on every traversal. So that's one example of things that we're thinking about. Ali, were there any others that you think are good to discuss?
Yeah, there maybe just abstractly there are a bunch of algorithmic optimizations that that are, some of them are come from the network verification research that are going to be helpful here as well.
Okay. So are there any particular sort of guarantees or maybe any holes besides what we discussed with regards to stateful elements that you think might be inherent to this particular method? Like what kind of coverage we should expect and should not expect with this tool?
So there is one thing that is not inherent to the approach, but well, there is a maybe caveat or a way that we deal with non-determinism. We're dealing, like in our current implementation, even though the approach can it does not, the overall approach doesn't have this limitation, or but our implementation has this limitation that for things that lead to non-deterministic outputs. For example, things like like ECMP. ECMP, like which, if you have a group of possible ports that you can select, the port that will be selected is effectively non-deterministic for our purposes and use cases. And in these cases, basically the way that we model it is that the packet can take any of those ports. And this sometimes basically makes some of our notions of coverage unsound, in the sense that, for example, if you are requesting to generate a packet that, for example, hits a certain egress ACL that matches on a specific port, then P4 symbolic might generate a packet and tell you that, oh, this might hit that egress port, but because of ECMP, maybe in an actual implementation, the packet might take a different port as output. And so in such cases, we basically we do not our notion of coverage basically has this hole that it may be unsound. The way that we solve this problem is that we consider all possible, for the expected output part of it, we consider all possible. It doesn't solve the notion, the coverage unsoundness, but at least for testing purposes, what we do is that we consider all possible all acceptable outputs as a valid output. When we're doing this diff testing, basically, if the ECMP group says that, okay, ports 1 and 2 or either one, port 1 or 2 or 3 will be selected, what we generate as expected output is that port 1 or 2 or 3 will be selected. And if the actual switch generates any of those packets, like if it generates a packet that goes out of any of these ports, we will consider it as a valid output.
Wow, very nice. How do you know it's a CMP? Is it you're looking at specific P4X terms to sort of make this determination?
Basically, I'm trying to remember. If you have it's more so in P4 basically the notion, like the way that this is modeled is a bit more general than just CCMP. There is basically we have this notion of action sets instead of one
Actions,
action.
yes, action
Basically,
selector.
a set of action can be selected, and the way that we model it is that once you have an action set, you say that any of these actions could be selected. Basically, yeah,
I see. It's called action selector, I think.
action selected. Basically, yeah.
Very well. So I guess one other thing I want to just say maybe as a comment, but you can confirm, is that this approach generally requires to have an equivalent control plane interface, right? And I believe in your case, this is completely true. So you use the same P4 runtime interface to load the tables onto each of the targets, right? Be it the hardware test bed or the P4 switch simulator.
Exactly, because
But
our switches basically have our switches. Our switches stack supports P4 runtime interface, so we'll use the same interface to program the tables on our switch as we use in our simulator BMV2 basically.
so that really requires people to have, if they want to test the hardware, that hardware really has to implement exactly the same P4 program in the same architecture with the same control plane interface as what you run on the simulator. And you had a huge investment in making this done, right? It's not something that people can achieve on their own outside your
Well,
environment.
that's true, but also I don't know if it's a huge problem or not. That maybe it's more of a speculation. I mean, there are a bunch of table entries, and there needs to be some driver that converts those table entries in whatever format they are, for example, P4 runtime, into some other format. Now, somebody needs to create that basically conversion. Maybe that's not very trivial. But the good thing is that diff testing will catch it if there is a problem. So,
Absolutely.
yeah, so
You just
yeah,
need to create this infrastructure. That's what I'm onto.
that is
Uh,
true. That is true. Also, one maybe it goes into a little bit of nuance. For example, not everything that affects forwarding in our case goes through P4 runtime. For example, we have some open config GNMI configurations on the switch. Those sometimes, in some cases, not all the cases, in some limited cases, those things also affect forwarding. And for example, if we want to give you a concrete example, the packet recirculation, basically the loopback,
mhm.
the ports that are in loopback mode today are configured through GNMI in our case. And for these cases, what we do is that we go and look at that GNMI configuration and convert, like we have some auxiliary tables modeled in P4 that basically kind of reflect the effect of those configurations in P4. And we have code that basically goes and looks at the GNMI configuration and generates these auxiliary table entries that basically simulate the effect of those things. Again, the nice thing, I know that I repeated this 2 times. The nice thing is diff testing. The point is to test between 2 implementations, and all of these things will be caught basically. Any problem in any of these processes will be caught using a diff testing based approach.
Well, thank you guys very much. So looks like in conclusion, as long as you have two targets which speak the same control plane interface and where you can inject packets, this is the tool that allows you to prove if these targets, or at least make sure that these targets work exactly the same way, correct?
Yes. Yeah. So I think one of the key points that make it a much simpler problem for us is that we focus on testing and validation rather than verification. Verification is a much harder problem, but testing is definitely much more tractable.
Wonderful. Good luck, and thank you for doing such a great job. Congratulations. Thank you.
Thank you. Thank you for your time.
Thanks for having us.
Thank you.